One other thing that we know in this kind of benchmark assessment of how things might work is that there's considerable anisotropy, meaning that if we look at the conductivity in a vertical dimension, so we take, let's say, this saturated hydraulic conductivity, and we think about the hydraulic conductivity vertically, and we think about the hydraulic conductivity laterally, if we're in a textbook-like system that's isotropic, meaning it's the same in both directions, in forested catchments, we often have highly anisotropic systems, where if you go out with your handy-dandy measurement device for hydraulic conductivity, and you make the measurement this way, and then you make the measurement this way, they could be radically different. This can really enhance the nature of lateral flow down at this interface. If things are conductive at a certain rate this way, but are much more conductive laterally. This has a lot to do with the way soils might develop, catenary sequences that we might see, and maybe more importantly, biological activity that might go on. So this is also an important consideration, as is this one, for thinking about this transient saturated flow. And it can be highly preferential. This is a slide from Roy Seidel, who's now at Kyoto, and showing you kind of a cartoon of what this might look like in a forest setting. But if one really exposed the soil profile and looked what the soil is made up of, one would see this incredible kind of preferred flow paths that exist in the soils that we often work with. So this can be highly preferential, which aids and accelerates the type of lateral subsurface flow behavior that we might see. Okay, so moving towards kind of a summing up of this introductory section here. This is a slide in the Dunn and Leopold text, Water and Environmental Planning. And this, I think, is still really a good way to kind of think about this in a gross conceptual way. If we look at this axis, this is kind of your climate, vegetation, and land use that you might have. And in these arid, kind of subhumid climates, disturbed areas, these are the zones that are where infiltration excess is dominating the storm hydrograph. But again, it's important to recognize it's not one or the other, because in many of our catchments, all of these things could be operating. It's maybe identifying which are the dominant processes. And then this variable source area response, whether it's direct precipitation onto this expanding and contracting source area, producing saturation excess, or subsurface storm flow, largely depends on what the topography might be in terms of whether or not these are concave foot slopes, wide valley bottoms, the kind of textbook example like I showed in one of the earlier photos, or steeper, straighter slopes maybe where there's more opportunity for lateral flow. So this is, I think, a good way to conceptualize in a really general way. Now, I mentioned that what made the variable source area theory great is the fact that it was formalized into a computer model called Top Model. This is by far the most popular conceptual rainfall runoff model in forest hydrology out there. It was developed in the mid to late 1970s. Keith Bevan, who's now at Lancaster University in the UK, and Mike Kirkby at Leeds. And Bevan has made a career of really looking at uncertainty in hydrological modeling and how one couples processes and model concepts. But it's very appealing to us in forest hydrology because it's really variable source area based. It identifies this zone around the stream that's quite dynamic. It also notes that we can have subsurface storm flow and uses this topographic index where at any point in the landscape we compute, again, the upslope contributing area and the local slope angle, and this then would be the topographic index going from very small number to a large number at the outlet of the catchment. And if you're interested in working with this model, it's freely downloadable. Type Top Model into Google. You get a variety of things that come up, but you can certainly make your way to the computer code in forest hydrology. Now, there are four main assumptions, and this is the way that these have been captured in an algorithm-like way. And I'm not going to go into all the the details, but I just want to say how this is a clever way of kind of wrapping our arms around these processes that we've talked about. First of all, the so-called Dupuy-Forchheimer assumption that the groundwater table can be expressed by the surface topography. That is, water table is kind of flexing up and down across the forest watershed and roughly approximates the topography of the topographic surface. Big assumption, and we'll see it's violated a lot in practice, but this was a way to dispense with a whole bunch of gory details and to enable this model to only have 4 or 5 tunable parameters. So this isn't like, models you might be aware of, HSPF, the Stanford watershed model. I mean, those are models with a gazillion tunable parameters where you're tuning dials and you could have the right answer for a million different reasons. This is a much more appealing, I hope no one's using those models here. No, they have certainly a place and a use. But this is appealing in forest hydrology because while it's simple, it's really tuned into the dominant processes we think operate. So here's the topographic index, increases in a downslope direction. We can compute it directly off a topographic map. Most states now have 10-meter DEMs, freely downloadable from USGS. And then the depth of the water table is assumed to go from really deep at the ridge to 0 at the intersection with the saturated area. And the last assumption is that this transmissivity, which is the hydraulic conductivity times the soil depth, decreases exponentially with depth. Now this is the most clever assumption of all, I think, because now it says that we don't need to know soil depth over our forested watershed. Soil depth doesn't really matter because the deeper you go, this just kind of becomes asymptotically closer and closer to 0. So really, all the action's happening up here, and what you're really doing is just dialing in the right shape function for this decline that you can actually go out and measure, and then you don't have to worry about how big your control volume is, how much, how deep your soils, your saprolite or till or whether geological material might be. And then here's just a map of how one would express this topographic index from a DEM. This is a 4D plot, meaning I've taken a 3-dimensional diagram and I've draped over it this topographic index. So for each of these pixels, these are 5-meter pixels in a 4-hectare basin, and now each of these pixels we've done this very simple upslope area, local slope angle calculation. And as you saw, this can be a very good first approximation of wetness distribution, saturated area distribution, and it's a good starting point. Okay, let's look in some detail now at the plot scale. So what we're aiming to do now is delve into some of the details that we've kind of set up with this overview of runoff processes. We're going to look at what are the first order controls on how water might move vertically at the plot scale. And we'll look at depth decline in certain features, things like drainable porosity, the depth decline and hydraulic conductivity that we just spoke of. And then we'll look at preferential flow, because what you'll find is that while this kind of macro porosity, these more preferred flow paths, make up only a small percent of the total soil porosity, they can really account for most of the flux when it's wet. So these are the things I'd like you to take away from this section. So we're going to look at first what goes on in the matrix that we might get from the typical measurements that we'd use, and then look in terms of the preferred flow that we often have great difficulty in defining. So if we take kind of a generic forest soil and we look at a profile, this is 0 to 1 meter, and we look at the profile development, we know that there are changes with depth in the soil. One that we talked about was hydraulic conductivity, permeability high up near the surface, decreasing with depth. Bulk density low here, much more compacted at depth. Total porosity might change in some way with depth. And it's this depth function that we're going to look at, because the shape of this depth function for some of these important parameters really influences whether or not you're going to get this zone of temporary saturation at some place in the profile that's really the driver then for lateral flow at the hill slope. So what we're going to look at is drainable porosity, which I'll define in a couple of minutes, bulk density, hydraulic conductivity, and pore size distribution. And we'll look at some data from different soil profiles, mostly forest profiles, to kind of think about, first of all, the matrix that the preferential flow is embedded within, and how that might change with depth. So here are some data, and maybe we'll look at this and then take a break, because this data is going to require a bit of caffeine-enhanced concentration. For me too. So here are some data going from near the soil surface, this red line. Let's just take the plot on the right-hand side. And what we're looking at are moisture release curves, which is the relationship between water content and pressure potential or matrix potential. And the red line is a soil core taken from near the soil surface. And then these lines represent cores taken deeper and deeper into the profile. This purplish, whatever color that is, magenta one, is down around 3 meters or so. Now what do we see? Well, when we start at saturation and then drain this core, we get a big decrease in water content with a given amount of suction applied. This is a moisture release curve, or a water characteristic curve, a PF curve. You've probably seen this before in other ways. I know these 3D diagrams are kind of tough to interpret sometimes. But what do we see when we move with depth? What's happening here? Kind of flattening out, isn't it? And what's really happening is that the distance between, say, this point and this point in terms of water content is becoming less. At saturation, this is the porosity of the soil, 60% by definition. And what this is saying is that in the near surface soil, we've got a lot of storage potential in terms of the distance from here to here, but deeper into the profile, we've really squished that available storage, because we've decreased a little bit the porosity, but this squishing, this flattening of the moisture release curve, we're calling the drainable porosity. So this distance in volumetric water content between 0 and minus 100 centimeters of water, which is kind of like the wet part of the moisture release curve, defines the drainable porosity. And in the shallow profile, the drainable porosity is very high, but as we move to depth, the drainable porosity becomes quite low. And I'll end with this one. So this is now taking that data and now taking those distances, which we're defining as drainable porosity, and showing you how for different soils in different places, this drainable porosity changes with depth, often in a very nonlinear way. What it means is often we only need to get a very small amount of water to depth to create saturation, because there's so little storage there to begin with. Whereas up in the shallower soil profile, there's a lot of storage for incoming rainfall. This is where preferential flow, that we'll talk about after the break, becomes critically important. Because if we have some preferential flow pathway to get water from the surface down deep, we only need a little bit of water to penetrate along a decayed root channel, an animal burrow, or something to bring this area to saturation. And that's why often water tables develop very flashy at depth. This is very important for slope stability, but for runoff generation, this is often the hot spot where runoff is generated. Now, this notion that hydraulic conductivity declines with depth is important as well, because then as water tables begin to rise into the more conductive soils, that's when we can also enhance lateral flow towards the stream channel.